Shall we do? I like that. I like that little reference to 6.4. I like that.
A throwback.
Hello and welcome back to Calculus 2, section 6.5 on lengths of curves. So we should have this concept in general that if you have a cord of some sort, a rope or whatever, and you want to know what the length of that thing is, right? You stretch it into a straight line and then you measure it. So that's not an issue, right? Anything that you can stretch and measure, just use the straight edge and you are done. Now, the problem arises when you are not... How is this tangled now? It tangled to the two cords that are... Whatever. Anyway, so the problems arise when you cannot stretch the line that you want to measure. For instance, a road or something that it's made out of glass or whatever, right? If it's made out of metal, you just heat it up and bang, 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 and there you go. Well, glass you can still heat up and whatever. Can't stretch. All right, that's it. You don't have tools, you can't stretch. So we would like to know. Now, one of the project problems that revolves in that pool of problems that you might get within 2 weeks says print a graph of a function so and so between the numbers so and so, and then bend the piece of the wire to mimic that function. Let's say it's a square root of x or ln x or whatever. Bend the wire along that, right? And then cut the wire to actually be the same length as the one that you printed on a paper. Then use the formula to compute the function that you, right? And then stretch the wire and use the ruler, use the proper conversion units, and then you have, you can see that what you measured, if you did everything correctly, and what you calculated, like within reasonable error of like 1% or whatever, is going to be the same. So one of the problems could be that. One of the problems could be, we talked about the cup or egg or whatever it is, right, to find the volume by rotation. So, you know, these project problems are something that you actually get to play with and work with your hands to take pictures as well. The report is going to have the write-up on the method of measuring and what you did and so on. So it's just tons of fun, right? That's like, you know, putting all of these concepts to life. So now, what is the goal of lengths of curves? We want to learn the formula, which will allow us that if we know the function for the curve that is presented to us, we can calculate the length of that curve. So now you know how to calculate area under the sine curve from Calculus 1. You know that area under sine curve is 4 between 0 and 2 pi. Now you will be able also to calculate the length of that curve from 0 to 2 pi. You will be able to calculate lengths of any curves. Now, how does this work? Why does it work? And let's see. So now what I'm going to do here is I'm going to have some random function, turned out to be square root of x, but whatever. And I'm going to say, let's calculate between a and b. So I'm going to have a representative rectangle delta x. It's a little bit wide, but that's okay. And if you zoom in onto this little part, we're going to have a curve, and then we're going to have our delta x come in with the 2 points, and now observe that my approximation is a straight line. So this is not exactly the curve that we need, but it's pretty close, right? So now, if you observe this triangle that you get, you have delta x over here, and you have delta y. Let's use the delta x and delta y, the proper ones. And this length here is going to be, I'll call it lowercase l, is going to be the Pythagorean theorem delta x squared plus delta y squared, if you use the Pythagorean theorem to calculate the length of the hypotenuse. Now this is for one of infinitely many rectangles, and we know how to deal with these things when we have many of them. We plug that into the integral, right? So you get that limit and summation and all of that kind of good stuff. So now what I'm going to do is I'm going to say, well, we are going to have limit as n goes to infinity, the summation 1 to n of the square root of delta x squared plus delta y squared, all of that times delta x. Now this is the Riemann sum form, so this can be easily converted into integral a to b of the square root of delta x squared plus delta y squared delta x. So now, what am I going to do? Right? What do I do with all of this? Actually, hold on, I don't need this delta x here. Oops. I don't need the delta x because delta x, let's solve this, erase the integral part. Let's solve this L part. So L part is delta x squared plus delta y squared. What I'm going to do is I'm going to factor out delta x squared inside and get 1 plus delta y squared over delta x squared. So when I factor out delta x from the delta y, because it doesn't have one, it will gain it in the denominator. And now this delta x goes outside and this becomes 1 plus delta y over delta x, everything squared, times single delta x at the end. So now you can see that the length of the curve, when you add infinitely many of these guys, is integral a to b, square root of 1 plus the derivative squared, right, delta y over delta x, the derivative squared, and delta x and dx are the same thing. So that's the way to derive the formula, and this formula will be upgraded twice in Calculus 3. So for parametric form and a polar form. So there's the length of the curve. So now we can calculate lengths of curves using this formula. Now, be very careful. You can't do this on every function you can possibly imagine because you don't know how to integrate all of the functions that are out there, right? So please stick with homework problems. Those are written with care, right? Knowing that you don't know chapter 7 yet. You don't know integration by parts, you don't know trig sub, you don't know trig integrals, you don't know integration by partial fraction decomposition. So since you don't know these new methods of integration, you are only limited to basic integrals and u sub. And pretty much 100% of your integration in this section is going to be u sub, right? So stick with homework problems. Now I'm going to jump into homework and take a look. By the way, lecture is over. I'm just going to write also the length in the y direction, and now we just do examples. There is nothing else. The title is length of curves, and there is the formula to calculate length of the curve. We could talk actually of the dimension of the dimensionality of this equation, because you are used to integral to give an area, right? Well, previous integrals were giving you volume, and I showed you the 3 dimensions. Length is one-dimensional. So this integral here better be one-dimensional. And it is, because the square root and square roughly cancel. They don't cancel because of 1 plus. But when you are considering the order of magnitude, they do cancel. So the square root and the square cancel each other out. And then you have integral of the derivative. That cancels, leaving just this puppy behind. I'm sorry, not the function, right? Leaving the function behind. You know that the derivative of the integral, it's plugged. Oh no, it's not plugged in. The derivative of the integral, don't go far, in your fundamental theorem of calculus is canceling, right? So this is actually integral of the derivative. That's the same thing, right? I'm still here.
Where'd you go? Class is over, I guess.
Here. So the other formula that I should write at this time is that L could be also C to D, square root of 1 plus f prime squared in terms of y dy. Right? That's if you have it in a y direction. So there is no rotation here, no areas, none of that stuff. You just have a function that has that line, and then you're computing the length of that line, and that's it. Call it a day. So that's all that we have for the theory for this, and now we'll just go and do some of the problems. So they're called arc length calculations. It's just the length of the line. So let's see what they have to offer. Problem number 8. We'll do 2 of these and call it a day. So y is equal 4 minus 3x on interval -3 to 2. I love the fact that in parentheses they say use calculus, which is actually good direction because you shouldn't be using calculus for this problem. It's a straight line, right? If it's a straight line and you have x1 and x2, compute y1 and y2 and just run the distance formula between 2 points, right? Yeah. So this problem can be done in middle school, right? You know the middle school formula is like the distance formula. So you should be able to do it. But they say use calculus, which it's forcing us to use our formula, right, boxed in red. So let's do it. I need the derivative, and that's y prime is equal to -3. Great. And I actually need f prime squared of x. So that's +9. So my length of the curve is the integral a to b x. Nice. That's the integral of square root of 10 dx. And it's the square root of 10 x from -3 to 2. That's root 10. And then I have upper limit is 2 minus the lower limit -3 gives me 5 root 10. So the length of this curve is 5 root 10. Observe that I find the derivative on a side. This is like one of the rare occasions when you will be seeing the derivatives in this class, right? In a course. We might have like 4 or 5 sections only with derivatives. Power rule, right? Yeah, most of them. Well, this was the basic one, right?
Power rule, yeah.
Chain rule is the most frequent one.
Also that one. Wait. So on that, you know how like, usually we plug in the top interval and the negative, the top is subtracted by the bottom?
Yes, top minus the bottom. Good. I got it.
Pretty good.
That's not ninja-like.
Not at all.
Hearing from miles. Let's see something spicier.
One more allegedly.
No, then we have a next section.
Oh, see, alleged.
So 12, the function is given as 3 ln x minus x squared over 24. That's beautiful. on 1 to 6. It's amazing. Okay, we know where to start. Find the derivative first, so you can put y prime, f prime, dy, dx, whatever makes you happy. So derivative of ln x is 1 over x, so this is 3 over x, minus the derivative of x squared is 2x, so this becomes x over 12. Right, because 2x over 24, so it's x over 12. Great. L equals integral from 1 to 6 square root of 1 plus open parenthesis 3 over x minus x over 12 squared dx. Yeah, we gotta integrate this. I'm just looking at your faces right now. Take a deep breath, let's go. The only thing that I can do in this case is clearly square the binomial, right? Now, when you are squaring the binomial, please remember the middle term, because that's the one that makes all of this possible. So, when you are squaring a minus b, you will have a squared minus 2ab, middle term, plus b squared. This is the formula for square of binomial, which we can use to quickly work on that. So, we start with the integral 1 to 6, square root of 1 plus, and then you have 9 over x squared minus, and then we have,
Oh!
There we go. I was about to say, you have to.
I forgot to put it down.
Oh.
I was following along.
So now we multiply these two. X's will cancel. 3 and this will cancel. Times 2, we get a half. Did you follow that? Let's do it on a side. 2 times 3 over x. Well, it's going to be negative. And then you have x over 12. So x and x cancels. 2 times 3 is negative 6 over 12 becomes negative 1/2. Are we all agreeing on that? So that would be the middle term from our expansion, negative 1/2. So all of x's, everything is gone. And then we have plus x squared over 144, close parenthesis, dx. The only thing that you can do now is what? That's the second option because it's still easy.
Plug in 6, and then subtract it.
Hold on, we didn't integrate yet.
Or I found the integral. So instead of square root, you can just do all of it in parentheses to the half, right?
No, not yet, not yet. What is the only thing that we can do now? Yes? No. What's the obvious calculation that you can do?
The 1 and 1/2.
1 and 1/2, thank you. So, yeah, I know. That was such a calculus question, right? So now we combine like terms, which is 1 1/2 over here. So 1 minus a half is a half. Keep it in the middle, all right? So we have a square root of 9 over x squared plus 1/2 plus x squared over 144 dx equals to integral 1 over 6. Are you ready for a $1 million move?
Oh.
What's the $1 million move now? $1 million move now is for you to realize that this expression here and this expression here are the same except the sign of the middle term. Do we see they have the same numbers?
Yeah.
And it's just that 1/2 is negative or positive, right?
Yeah.
Now, if I go back to my square of binomial red formula over there and change this one over here into a plus, then this one over here changes into a plus. Which means that if I am to compress this, it will compress into this one over here with a plus. See that? I know, right? It's awesome. So, when you compare these two guys, they're identical except the sign in here. Now, that sign is on the middle term, and the sign on the middle term is the one that decides which sign you get here. So, if these two are the same, if this spawned this, then this has to compress into that with a plus. Yeah. You got 6 of these problems in your homework.
Pretty good.
And then the next section as well.
No, I thought you said you was calling it a day. What the hell?
I know.
What is that? I don't think that was the... He said it like every other sentence. What?
So 3 over x minus x over 12, and now it's a plus and it's a square. Dx. So what is obvious now? The square and the square root die. And the only thing that you need to integrate is the integral of 3 over x, that's a joke, plus x over 12, that's a joke, dx. Yeah. This is called mathematical gymnastics, right? And then you score anywhere from 0 to 10 points on the gymnastics, depending on how many flips you do properly, like a triple thing and triple backflip. Is that a thing? Triple backflip? I don't even know.
Try it.
Why?
You want to see if it's possible.
I'm in equilibrium right now. There is no reason to move unless there is a bear or something. So.
He said move.
I said move, but that's okay. Yeah. So now integrate 3 over x. Well, that is 3 times ln absolute value of x. Make sure you put that absolute value there. It's not there for decoration, right? We need it. Plus, the integral of x is x squared over 2, so this becomes x squared over 24, calculated from 1 to 6. And that's going to be equal to some number.
Pretty good.
And that number is the length of the curve that you are looking for. So these are the more spicy examples. Now, most of these problems are applied problems for your engineering. The civil engineering, calculate the length of the arc. You have that stuff in your lab if you care about it. Use the software. I mean, integration, apart from these gymnastics that we just did, can be very nasty when you have the trig functions that have the decimal inside and so on. So you have a whole bunch of these problems that have not so fun integrals to work on. I am just going to copy. I'm not going to do this problem. You will eventually know why. But I'm just going to copy problem number 10 and give you that the function f of x is given as 1/2 e to the x plus e to the minus x. And then I'm just going to put a smiley face over here. And then eventually you will know what this means. Yeah. Eventually you will know why I put the... Because when you go and do this problem by hand, right? You guys are going to spend like 30 minutes to solve it, and you will get it, and it will be perfect, right? And that's awesome, right? When you are done, right? And then eventually in this class, next week, I will do this problem in 2 lines. But we are not there yet. This is what mathematics is all about. I see Matt over there is smiling and like inside he's cracking up, but on the surface he's trying to be polite, all right, because he's a nice guy. But he knows exactly why I wrote this, because he knows what this is, right? So this problem is going to take 2 lines in the future, right? Right now, when you go home, it's going to be, it's good for carpal tunnel and killing time and stuff like that. So you can practice. That's 6.5. We'll take a short break, and we have 6.6 when we come back. Surface area of revolution, which is this formula upgraded a little bit. So it's a very short section.